I just wanted to start by saying good afternoon, everybody. Welcome to the latest Iris Core Program webinar. This is your host, Andy Frisetto, aka the Iris Swiss Army Knife, speaking to you from the Incorporated Research Institutions for Seismology headquarters office here in Washington, D.C. If you're not familiar, IRIS is a almost 30-year-old consortium of universities and an NSF-funded science facility operating programs that enable a broad spectrum of advanced research in geophysics, particularly seismology. And today's webinar is one of the more research-focused ones that is uh, designed to highlight the scientific results that are either directly enabled by facilities that IRIS operates or represents important work from one of our partner organizations. And just with respect to the webinars, they're all recorded. So it's recording right now. They're archived on our YouTube channel, which is, I brought this up here on the window. Iris ENO is the name of our YouTube account. And if you search down to webinars and other long lecture formats, you will see this webinar pop up on here within, hopefully this afternoon, but definitely within a couple days. Also, I wanted to just point out the upcoming webinars that we have. I've been working to try to get this schedule mapped out a little bit more in advance than I have in previous semesters, I guess you could call it. And so we have our speaker today, Caroline, and there's also Burke Briol, Heather Deshawn, Stephen Hicks, a group of a few people from NSF, and then Maggie Benoit and Marianne Carplus with a wide variety of topics as the spring transitions into summer. So I hope that you'll definitely be joining us for some, if not all of these, and of course they will be archived for future enjoyment. Just to go over a few of the ground rules, only the presenter and I are going to be speaking today. I'll unmute Caroline in a second once I finish the introduction. So if you have a comment or a question as the webinar is unfolding, just clearly type it into the box that's on your control panel. And at the end, I will read the name of the person who asked and the question, and then Caroline can answer that for you. If a question has been asked more than once, if there's several of these similar questions that have been asked by the time I get to the first one, I will probably just sort of try to bundle them all into one question. And if I've already done that and that question comes in again, I'll just skip it so we don't have too much redundancy. If the webinar crashes, this has only happened, well, I think it's happened twice now in almost 30 webinars, but uh, we're capable of rebooting it, so it's not the end of the world. What you would do is give it about 30 seconds while I reboot on this end, and then just click the link in the email that you received your registration information on for this, and it'll bring you right back into this like nothing happened. Also, this is mostly for my curiosity. It's good to know if you're in a group of people watching. So I can count the number of people that sign in as single users. But if you're in a room watching this with a group, just let me know how many people are with you. You can either write that into the little question box and send it to me as a message, or just email me afterwards. It certainly helps. So I think without further ado, I want to introduce our speaker today, who is Dr. Caroline Beghein. She is an assistant professor at University of California, Los Angeles, where she has been since January of 2008. She received her PhD at the University of Utrecht in the Netherlands in 2003 before she moved to the US for research appointments at MIT and Arizona State. In addition to her research, which you'll be hearing about today, Caroline also served on the Global Seismic Network Standing Committee. So I just want to thank her for her service to helping the IRIS organization as a whole. I think without further delay, I will introduce Caroline to present her talk, New Constraints on the Nature of the Gutenberg Discontinuity from Anisotropic Seismic Tomography. And so, Caroline, I'm going to unmute you. And actually, what I will do is I'm going to shift screen control over to you now and then unmute you. And you should tune in right around now. You should be live.
Okay. All right. Can you see? Can you hear me?
I can, and I can see your slides.
Okay, wonderful. Okay, well, thank you for inviting me to give this webinar. This is also the first time I actually present these results, apart from a brief introduction during the last AGU meeting. And I want to acknowledge my collaborators on this, who are Kei-Ching Yuan and Zheng Xing, who are my two graduate students at UCLA, and Nicholas Schmer, who has been working with me on this and is at the University of Maryland. So as we probably all know, plate tectonics is the idea that we have plates dividing the Earth's surface, and they move with respect to each other, creating earthquakes, volcanoes, and mountains. And these plates are part of a lithospheric layer that is at the top of the Earth. This layer is very rigid, it doesn't deform very easily, and it lies on top of a more deformable asthenosphere. The boundary between these two layers, called the lithosphere-asthenosphere boundary, or LAB for short, is therefore a rheological boundary. And even though it's a fundamental concept, we actually do not understand very well what physical or what chemical processes dominate the origin of the lithosphere-asthenosphere boundary. And that's important to understand just how tectonic plates form. The lithosphere is often defined as a thermal boundary layer, in that it is conductive. Heat is transported by conduction inside the lithosphere, while we have advection in the asthenosphere. And half-space cooling models predict that in that case, the thickness of the thermal lithosphere should increase as the plate ages and moves away from the ocean ridge where it's created. And the thickness should increase approximately as the square root of time. This is supported by tomographic models of shear wave velocities, as we have two examples here. On the left, this is a model by Beghein in 2006, where we see shear wave velocities, perturbations, actual absolute values of shear wave velocities as a function of depth on the vertical axis, and as a function of oceanic plate age increasing from left to right. And we observe a low velocity layer that is below a high velocity layer, and the boundary, well, the limit between these two layers roughly follows a half-space cooling model shown by the black line. So it seems like velocity models from seismic tomography based on surface wave inversions agree with the idea that temperature is the dominating factor creating the lithosphere-asthenosphere boundary. There's the model here on the right by the Colorado group, Rayleigh and al. 2004. They show similar result with a low velocity layer and a high velocity layer on top. The only difference is that the bottom of their high velocity layer kind of flattened out after 80 million years old, which they attributed possibly to additional heat source. Now this cartoon is a nice summary by Fisher and al. That shows that so temperature, shown by the blue line here, can explain a reduction in shear wave velocity from the lithosphere to the asthenosphere. It can also explain a higher viscosity in the lithosphere than in the asthenosphere, which is what we would expect for a rheological boundary. But it also shows that other factors can also produce similar results. So melt or water can also create or reduce the viscosity in the asthenosphere or reduce velocities in the asthenosphere. So there is some uncertainty as to whether temperature is the dominant factor, or whether, for instance, water could play a role. And Karato and Jung in 1998 proposed that a sharp change in the water content of the rocks at the ridge, at the ocean ridge, could actually explain the formation of the lithosphere. They argued that creating partial melt away from upwellings is actually really difficult, and so which is why they propose that a reduction in the water content going from the asthenosphere to the lithosphere could explain the formation of the lithosphere. And this was supported by experimental evidence by Hirsch and Kohlstedt, shown at the bottom bottom right of the screen. There is a lot of studies that argue in favor of partial melt as a mechanism to create the lithosphere-asthenosphere boundary. These results from last year by Sakamaki et al. Were experimental results, experimental studies of the properties of basaltic magmas, and they showed that there is a density difference increase, but also a reduction in viscosity and a maximum in magma mobility between 120 and 150 kilometers depth. And so in this study, they argued that this means that melt are expected to migrate out of the asthenosphere and accumulate around 80, 100 kilometers depth. So this is an argument in favor of having melt at the lithosphere-asthenosphere boundary. Magnetotellurics studies also favor the presence of melt. This is a study by Naif et al. In 2013 that showed a layer of anomalously high conductivity between 45 and 70 kilometers depth, and they argue that partial melt needs to be present to explain this type of observations. And now, in terms of seismic data, well, there's receiver function studies. This is one by Kumar and Kawakatsu in 2009. There's quite a few of them in the literature. And receiver function studies detect a sharp drop in seismic wave velocities. That's usually associated with the Gutenberg discontinuity. And we see, so these are receiver functions that I show here, results, and we see that the data can be explained by a drop here, a very sharp drop in shear wave velocities at depth that are usually associated with the lithosphere-asthenosphere boundary. And in this paper, they proposed that melt pockets accumulated in the asthenosphere and horizontally aligned should be able to explain this sharp drop in velocity, and also would explain some observations of radial anisotropy that have been made in the past, showing that horizontally polarized shear waves travel faster than vertically polarized shear waves at depth associated with the asthenosphere. And finally, the observations of the Gutenberg discontinuities have also been made with SS precursors. And so this is a study by Nick Schmer in 2012, in which he used precursors to the SS waves, SS phase. So we have the SS phase here in black, bouncing toward the surface of the Earth. And these are the reflectors here that bounce at the Gutenberg discontinuity, and they arrive before the SS waves. So they have the advantage that the bouncing point is midway between the earthquake and the station. So these type of data sample regions where we do not have necessarily seismic stations. So they make them really good, ideal to study a plate like the Pacific plate, and it's a large plate without that is not covered by seismic stations. And in his study, Nick Schmer showed that the presence of melt is probably needed to explain large regional variations in the strength of these reflectors. And he argued that these reflectors enhanced near upwellings like hotspots shown here and here, and also near subduction zones. So the accumulation of partial melt near upwellings, or perhaps due to the release of water near subduction zone, might be needed to explain this strong variability in the detection of the Gutenberg discontinuity. Now, very interestingly, also, the data I used, the SS precursors, allowed him to pretty much cover the entire Pacific plate. So he was able to interrogate the Gutenberg discontinuity over the plate, and you see the gray squares that are shown here pretty much all over the plate are places where he made measurements but was unable to detect the discontinuity. The discontinuity was detected where we have the red, well, the circles, and also the other symbols. So we see that the Gutenberg discontinuity is not observed everywhere in the Pacific plate, which makes us wonder whether it is actually connected. It is actually equivalent to the lithosphere-asthenosphere boundary, because if it is the lithosphere-asthenosphere boundary, it should be everywhere in the plate, at the bottom of the plate. Another observation from these results is that the detections that are made near younger oceans are generally shallower. So the discontinuity lies between 40 and 65 kilometers depth in this region, while if we go toward older plate, around 80 million years old, the depth of this discontinuity is more like 70, 80 kilometers depth. So there might be an age dependence in the depth of the discontinuity, as we would expect for a lithosphere-asthenosphere boundary. However, if we plot, when he plotted these measurements as a function of crystal aged for all the measurements over the plate, it is hard to see a very significant increase in the depth of the discontinuity with the age of the plate. Over here, in toward the younger plate, they are shallower than, deeper than we would expect from half-space cooling models, which are shown by the solid lines here. And then they seem to be relatively flat as we go toward older oceans. So this made us want to look at this problem in a different way, and we modeled seismic anisotropy in the upper mantle using a new set of data, well, relatively new, that was obtained by the Utrecht group and published by Visser et al. In 2008. They had measured the phase velocity of Rayleigh waves for fundamental modes, but also for higher modes, up to the 6th overtone for Rayleigh waves, and also up to the 5th overtone for love waves. So this was a unique data set. Measuring these higher modes is tricky. They're difficult to separate, but they apply some statistical methods that allow them to obtain uncertainties on the measurements and assess how likely they were to have actually separated these modes. So they made these global measurements of phase velocities. The advantage of using higher modes is that they provide sensitivity to much deeper structure than fundamental modes alone. So this is a figure showing the sensitivity of these modes for Rayleigh waves to a parameter that relates to the azimuthal anisotropy or vertically polarized shear waves. We have depth on the vertical axis and sensitivity on the horizontal axis. In gray are the curves that show the sensitivity of the fundamental modes to anisotropy. So we see they're mostly sensitive to the upper 200 kilometers. And the different colors show the sensitivity of the different overtones. And you see that they provide sensitivity to much greater depth. And what's interesting for this study of the upper mantle, they also do help increase the sensitivity in the top 200, 250 kilometers depth. The first overtone has a nice peak around 200 kilometers depth. The second overtone in yellow has a peak around 150 kilometers depth. And the sixth overtone shown in blue here has peaks in the deep mantle, but also in the top 100 kilometers depth. So including these higher modes does help increase resolution. So we used their isotropic phase velocity maps for Rayleigh and love waves. We inverted them together to obtain a model of shear wave velocity and radial anisotropy. So these phase velocity maps are basically at each point of the phase velocity maps. The phase velocity measurement is a depth integral of the structure underneath, and so there's a nice linear relationship between phase velocity measurements and structure, the vertical structure underneath that point, which can be inverted. We inverted these data for shear wave velocity perturbations and radial anisotropy perturbations. Shear wave radial anisotropy is defined here as the ratio between the speed of horizontally polarized shear waves to vertically polarized shear waves squared. We did not invert for P-wave anisotropy and P-wave velocity and density because these are not well resolved, and we assumed, as it is often done in these studies, that they were proportional to shear wave velocity and shear wave radial anisotropy. And Visser and al. Also produced, in addition to these isotropic phase velocity maps, they produced anisotropic Rayleigh wave phase velocity maps. This is an example here for the second Rayleigh wave overtone at 50 seconds. And we saw these black bars represent the fast direction of propagation for Rayleigh waves at these periods. And the length of the bars, as well as the gray background, shows the strength of the anisotropy. And so we can go from anisotropy in the frequency domain, as shown in these maps, to anisotropy in the spatial domain to obtain a 3D model of vertically polarized shear wave anisotropy by inverting the similar linear relationship that relates the anisotropy in the phase velocity to parameters, elastic parameters that relate to anisotropy of vertically polarized shear waves in the spatial domain. Now, these data are also sensitive to two other parameters, B and H, that relate to the anisotropy of P waves. We did invert for them because our sensitivity tests showed us that we were better off including them, but they are not actually resolved, so I'm not going to discuss them any further. We did account for the effect of the crust. It's been shown in several studies that this is important for these type of inversions. We see on the panel on the right, these are sensitivity kernels for the third Rayleigh wave overtone at, let's see, 35 seconds in white and 78 seconds in red. And you can see by looking at the two red curves here, for the whole overtone, that sensitivity kernel calculated with prem, shown by the dashed red line, or by prem on top of which we put a realistic crustal model, we can have strong differences in the sensitivity kernel. So it's very important to account for the crustal corrections as well as possible because it affects the sensitivity kernels and therefore it's going to affect the resulting model. And we also applied nonlinear crustal corrections to the isotropic phase velocity maps when we inverted for the velocity and radial anisotropy. A few synthetic tests to show you what we can expect in terms of resolution. So these are synthetic tests for azimuthal anisotropy. We simulated 70 kilometers thick layers here with these an input model shown in white of anisotropy amplitude that would be decreasing with depth, and the fast axis of for seismic wave propagation changing by 90 degrees from one layer to the other. We made tests without noise in red and with different levels of noise in the other colors. And we see this test shows that we can expect to resolve approximately 70 kilometer thick layers for azimuthal anisotropy in the top 200 250 kilometers depth. The resolution is about 100 kilometers if we go deeper, and we were not able to resolve anything better, anything thinner than 70 kilometers depth. Now for the shear wave velocity and radial anisotropy model, the resolution, the synthetic tests were worse. One thing I forgot to mention is that when we inverted the isotropic phase velocity maps for VS and Xi, we only inverted the fundamental modes. We did not include the higher modes. We did try that, and it improved the synthetic test, but it also introduced additional trade-offs that led to inconsistencies in the models. So we decided to only invert the fundamental modes for VS and Xi, and that's the model I will show here. But the synthetic tests show that we can resolve about 100 kilometers thick layers for VS, but the resolution for the radial anisotropy is very poor, and we might be able to resolve about 70 kilometers thick for VS, thick layers for VS in the top 150 kilometers, but that's pushing it. For the azimuthal anisotropy, if I go back one more, we did include the higher modes, and we tested that they did not actually affect the models. They did not introduce significant trade-offs, so we did check that. So here is I'm going to show the models we obtained. So this is a slice at 60 kilometers depth. So we have in each panel I will show there will be the age of the ocean floor in the top right. The bottom right is the radial anisotropy, where red would mean horizontally fast shear waves. But again, the radial anisotropy is not well resolved at all. I'm just showing it because it's there, but I do not want to interpret it too much. The large figure on the left shows the shear wave velocity anomalies as the background color. So we have low velocity perturbations along ocean ridges and higher velocity perturbations elsewhere in the plate. The yellow arrows represent the absolute plate motion in the no net rotation reference frame. We have these relatively thick black lines represent age contours. So we are at 40 million years old here, 80 million years old here, 120, and 160 over here. The thin black lines that you see here, a little bit everywhere, they are ocean fracture zones that we use as proxy for the paleo spreading directions. And finally, the pink bars represent the phase direction for vertically polarized shear waves that we obtain from our model. So at 60 kilometers depth, what we see is that, well, near the ridge, we have a good alignment of our model with the paleo spreading direction, which there by definition is close to the absolute plate motion. But as we move away from the ridge and we look at older plate, like here around 80 million years old, we see that the fast vertically polarized shear wave direction does not align with anything really, not with the paleo spreading directions and not with the absolute plate motion. Now, if we go deeper, we see that clearly the shear wave velocity background starts to change, and the fast axis for wave propagation is starting to rotate, and here we become more parallel to the paleo spreading direction, so around 100 kilometers depth. Then if we go deeper, the fast direction of propagation for seismic wave rotates a little more. Here we are becoming slowly parallel to the absolute plate motion around 150 kilometers depth. And then we go even deeper. Now we have a very nice alignment of the fast seismic direction with the absolute plate motion. The background velocity is very weak at this depth, but this is where we are losing resolution for VS very strongly. So the uncertainties on the VS model is definitely probably large here. So this is the, so what becomes interesting with this model is when we look at how it changes, how the anisotropy changes with the plate age. So we have, I have a few slices here where we have the depth on the vertical axis and the plate age increasing from right to left. And what's interesting is when we compare our model with the location of reflectors. So in white are the reflector data from Schmer 2012 obtained from SS precursors, and the black symbols are from a variety of other studies. We see in this panel the amplitude, the strength of the azimuthal anisotropy. And we see that we have clearly a very high amplitude here for relatively young to mid ages. And what's interesting is that the reflector data seem to follow a minimum in amplitude shown by the purple, pink, purple color here. Now, if we go to the next slice, we see, so this represents the angular deviation between the fast direction of propagation for vertically pressed shear waves and the absolute plate motion. So we basically can define two layers here. The bottom layer, called layer 2, where the alignment of the seismic fast axis with the absolute plate motion is pretty good. And layer 1 on top is where the fast seismic direction does not align with the absolute plate motion well at all. And so we see that the boundary between layer 1 and layer 2 that we can follow more or less here, perhaps with the blue color, kind of follows roughly a half-space cooling model, which are the black solid lines. However, the reflector data, they do not follow this half-space cooling model. They are really located more inside the top layer. And even more interestingly, if we look at the vertical gradient of the fast seismic direction, this is what we get. So in red, depth at which the fast seismic direction changes very rapidly with depth. And in pink would be locations where the fast direction does not change as we go deeper. And so it's very interesting to see that we have here around 150 kilometers depth. We have a high gradient shown in red that corresponds to the transition between layer 1 and layer 2 in the older part of the ocean. So going from a bad alignment of the absolute plate motion on top to a better alignment below. But it's very interesting to see that inside layer 1 we have another high gradient, another, oops, excuse me again, okay, forward. And we see that most of the reflector data, they do fall pretty nicely on top of this other gradient in the fast axis. And now if we look at the not very well resolved shear wave velocity model and radial anisotropy model, we see that the shear wave velocity model does show a low velocity layer as expected and as seen in many other models of this kind before. That is, and this low velocity layer is below a high velocity layer, and the thickness of this high velocity layer seems to be following more or less a half-space cooling model. And again, these reflectors are located inside the high velocity layer and not at the boundary between the two. If we were to use the boundary between the two layers as the lithosphere-asthenosphere boundary, we would not say that the reflectors follow the lithosphere-asthenosphere boundary, and therefore they're probably not equivalent boundaries, not equivalent interfaces. The radial anisotropy model does not show any thickness increase of the top layer with age, and this has been seen before, but again, the resolution is so poor for the radial anisotropy that I don't think it's meaningful at all. But I just thought I would show it because it's there. So, oh yes, this is just a similar view, just shown. This is just a cross section between 2 points across the Pacific Ocean. I have the shear wave velocity model on top. Again, we have a high velocity layer here where the reflectors are inside which the reflectors are located, and we have a low velocity layer below. We have a high anisotropy amplitude, as an azimuthal anisotropy amplitude here in the pretty much in the middle of the plate between 80 and 150 kilometers depth, roughly. The fast seismic direction aligns really well with the absolute plate motion, where it's red over here, and it does not align with the absolute plate motion in the top part. And the gradient of the fast axes show a peak here, where the reflectors really nicely, with which the reflectors really nicely align. It's not too much the case here near the ridge, but there are probably resolution issues with both the reflector data and with the tomography model there. A few things we looked at trying to estimate some correlation or see if there's an actual relation between the depth of the Gutenberg discontinuity and what we see in our model. It's very difficult to compare these two data sets, well, this data set and this model, because of the very different vertical and horizontal resolutions. But so we did plot the depth of the Gutenberg discontinuity, shown by the circles are the data from Schmer 2012, and the other symbols from other data sets. And we plotted that versus the depth of the maximum in the gradient in the fast axis direction. Now, if we had a perfect correlation, they would fall along the white line, that is a slope of 1. And we see that it's not a perfect correlation because there's uncertainties in both the models and the data. But this is not too bad of a correspondence. We can fit a line of slope about 0.9 through these data. If we look at the minimum in the amplitude of the azimuthal anisotropy, it's very scattered. The uncertainty is large, so we can't say that there is really a correlation, even though it looks like it when we look at the cross sections. But what we find is that if we look at the largest gradient in the amplitude of the azimuthal anisotropy, then there's more, we can see more of a relationship between that and the depth of the Gutenberg discontinuity. Next is plotting the depth of the Gutenberg discontinuity versus the depth of the largest negative velocity gradient. And then here, clearly, the gradient in the shear wave velocity is located deeper than the Gutenberg discontinuity. And we also see that the strongest negative gradient for the younger parts of the plate are shallower than when we go toward the older ages and when they're clearly deeper. So there is an age progression in the velocity model that we can see in this plot. Radial anisotropy, again, not resolved, but and we don't see any correlation. There's really no correlation with the gradient in the radial anisotropy, and no correlation with the change in the sign of the radial anisotropy. But so it looks like there is a nice relation with azimuthal anisotropy, and that would actually possibly help us explain why the Gutenberg discontinuity is not observed everywhere, even with SS precursors that can sample most of the plate. So this was proposed, an idea proposed by Reichert and Allen earlier this year in 2014, where they tested different scenarios where they had on the left here a layer with anisotropy on top but no anisotropy below, and then the opposite on the right, and they tried different fast direction of polarization. Here it's the fast direction is left to right. In the middle panel, the fast direction points toward the screen. And they tested these different scenarios. showing that depending on whether the anisotropy is stronger in the top or the bottom layer, we can get different type of reflector observations. And so having anisotropy associated with the Gutenberg discontinuity would explain why we can't observe it everywhere, because then the detection strongly depends on the amplitude ratio of the anisotropy in the two layers and on the azimuth of propagation. Now, it seems like the Gutenberg discontinuity is not associated with the lithosphere-asthenosphere boundary from our results, and it is, if we want to try to interpret the Gutenberg discontinuity, I would argue that we might still need some melt in regions where the Gutenberg discontinuity overlaps with the lithosphere-asthenosphere boundary. Toward the younger oceanic plates, and possibly where we have upwellings, it seems like they roughly overlap. And these are locations where we might argue that we might have melt at the lithosphere-asthenosphere boundary or the Gutenberg discontinuity. Now, these melt would need to be segregated into tilted layers in order to yield azimuthal anisotropy. If they were horizontally aligned, as has been proposed to explain radial anisotropy, we would not be able to observe azimuthal anisotropy. So we need some kind of dynamical process that would tilt, to keep them tilted so that we could observe this anisotropy. But a scenario that we propose that's really inspired by the Garrity et al. Paper from 1999 that might help explain all our observations is the following. So we would have, if we had dehydration at the ridge where the melt separation zone starts, this would create a dry layer on top and a more damp layer below. And that would yield to a compositional boundary that could be translated away from the ridge as as the plate moves away from the ridge, it gets older. And so we could have a dehydrated top layer and a hydrated lower layer, therefore more deformable. And on top of that, cooling, just simple thermal cooling of the lithosphere would superimpose to this compositional boundary. And so if we have on the very top, above the Gutenberg discontinuity, above this compositional boundary, a dry layer with weak anisotropy, we may not be able to align anisotropy with mantle flow or paleo spreading direction because it's so dry. But below the Gutenberg discontinuity, the alignment with the paleo spreading direction may be possible if it's if the rocks are hydrated, and therefore it would be transported away from the ridge and yielding to frozen in paleo spreading directions. And then we have below this thermal layer, boundary layer, we have the asthenosphere, in which we have active convection and alignment of seismic waves with current mantle flow. So in conclusion, we have been able to look at stratification in the upper mantle using azimuthal anisotropy. And it seems like the lithosphere-asthenosphere boundary is consistent with a simple thermal model if we use a definition of the lithosphere-asthenosphere boundary that is based on the alignment of the fast seismic axis with the absolute plate motion. Excuse me. The asthenosphere, in this case, would definitely correspond to a low velocity zone with a high radial and high azimuthal anisotropy of about 5%. But the Gutenberg discontinuity does not seem to coincide with the lithosphere-asthenosphere boundary, at least not everywhere. And so the more likely explanation is that it is an internal lithospheric boundary, and it seems that from our model, we show that the Gutenberg discontinuity is associated with a change in azimuthal anisotropy, which could be due to dehydration at the ridge. And this explanation would, this scenario would also offer an explanation for the discrepancies in where the discontinuity is detected between different studies and why it's not detected everywhere. Okay, that concludes my talk. Thank you.
Thank you, Caroline. Appreciate it. It's great. So while people type in questions, there were a couple that were submitted earlier in the talk.
Mm-hmm.
And this is a question from Devin Gerzik. And his question is, were there any measurements of, these were from probably the first 10 minutes of your framing. Were there any measurements of shear wave splitting? Would they have been helpful?
Actually, so let me, can you still see my screen?
I can, yes.
I think I've lost my talk. Here we go. I'm going to try to get to a shear wave splitting slide that I have somewhere. Yes, I do. Here. So yeah, so there are a few shear wave splitting measurements. So this is a map that shows the white lines do show shear wave splitting measurements that have been made. Obviously, they're mostly made on continents, and so we don't have a lot on the Pacific plates. And the red bars represent prediction of shear wave splitting from our model. And the yellow lines are the measurements expanded in generalized spherical harmonics to make a more fair comparison with our model, which is a global model. And so we showed that at the global scale, at the scale of the entire planet, our predictions are actually much closer to shear wave splitting measurements than previous models had been. But you see that there are still some discrepancies here. And so there are two views. Would shear wave splitting measurements help? Yes, if you assume that all the anisotropy from shear wave splitting is coming from the depth at which the surface waves are sensitive. Now, if some of the shear wave splitting is coming from even deeper, larger depth, then by adding them as data, inverting the shear wave splitting with the surface waves, it could introduce some bias into the model, I think. So I like to get a model from surface waves and then compare with shear wave splitting data and consider them as a separate data set without necessarily merging them so that I don't introduce too much bias there.
All right. And Devin had another technical question early on that's probably become clear, but I'll still ask it. He was just asking, are horizontal shear waves perpendicular to vertical shear waves, but within the same plane?
Yes, I'm not sure I understand the question really. Let me think. Can you repeat the question?
Yeah, the question was, are horizontal shear waves perpendicular to vertical shear waves, but within the same plane?
Oh, I see. Yes. Yes, if you think of shear waves as two directions of polarization, horizontal polarization and vertical polarization. And so if you imagine a shear wave that would propagate in the horizontal plane, then you have a vertical. I'm making signs with my hands, and of course nobody can see, but you would have a vertical direction of polarization that's perpendicular to the horizontal direction of polarization. I don't know if that's answering the question.
I think it makes sense to me. So next question is from Luciana Astes, and Luciana is wondering, where is Beghein et al. 2014 in press?
I think all I can say is that it's under embargo right now.
Gotcha.
So
But
soon, it will
coming
be
soon,
out
yeah.
soon, very soon.
Okay. Next question is from Ling Chen, and Ling is asking, is there any relation between the G discontinuity and the intralithospheric discontinuities that is observed beneath cratonic regions?
Oh, that's an excellent question that I've been wondering lately. I don't know the answer to that, but it seems like there is a discontinuity in continent, at least in cratons, and then now, here in the oceanic lithosphere at about the same depth. And we actually have another paper that's under review that's modeling the anisotropy of horizontally polarized shear waves as opposed to vertically polarized shear waves here. And we see that there is also a change in anisotropy in horizontally polarized shear waves at about the same depth. And which makes me wonder if it is a global feature, if it is connected. I do not know if there's a relation to that. This is something that I would hope I and other researchers will be working on not too long. That's a very interesting observation.
All right, great. I had a question on this. When you use receiver functions to look at structures like this, it takes at least a few years to get enough good events, good enough sort of event station pairs
Uh-huh.
to be able to do imaging. How long did it take to get the fold of data to do this work?
Which data?
For the SS, I guess I would say.
I guess
Yeah.
that's a question for Nick Schmer.
Oh, okay.
Yeah, he's the one who did those measurements. I don't actually know how long how, how long of a data set he used. Yeah, I don't know.
Okay, yeah. I'll I'll,
He's in
I'll
the
ask Nick.
audience, so he can write.
All right. So there's another question from Zhao Zhang, and Zhao Zhang writes, "Thanks, Caroline, for the great talk. I noticed that in Schmear's map of the G discontinuity depth, there are two groups, one in red, depth at approximately 50 kilometers, associated with younger Pacific, and another group in yellow, which is at a depth of 70 plus kilometers under older plate."
Yeah.
And then his question is, but in your explanation in the last slide, the G is at the same depth everywhere. Are they inconsistent?
So, well, first in the, can everybody see my screen still?
Yes, I can see it.
Yes. Okay. So in the map here on the left, so this is the mean of the measurements. But if you look at the panel on the right where we have uncertainties, then it becomes more difficult, at least to me, to say that there is definitely a change in the depth of the G if you account for uncertainties. And then even if there is an actual change in the depth of the Gutenberg discontinuity, if it is definitely a difference, if there is a significant difference between yellow and red, which I think Nick would argue there is, we have to remember that um, the Azimuthal anisotropy model has some limitation in terms of vertical resolution, and so I would not, I would not completely discard that if we had a very, very high resolution model, we would be able to see these small variations, but it's really hard to tell because it's very hard to compare, quantitatively these different types of data, basically. So I wouldn't say they're incompatible. If we were to put uncertainties on our model, which we hope to do in the near future, and we have uncertainties on these data, they may overlap.
Okay. Next question is from Amir El Sharkway. And Amir is asking, what about joint inversion of receiver functions and surface wave tomography? Is it possible that that would present more consistency on the G discontinuity?
Yeah, that would be definitely something we'll probably be working on in not too long. That would be an interesting exercise. Uh, it kind of, I mean, it, it it could also introduce some bias by doing that. I don't know. This is something we'll be trying, but I don't know whether it would change. How it would change the results really. What I find interesting here is that we had two completely independent data sets and models. And just by comparing them, we found this nice coincidence. If we had inverted them together to start with, I don't know if we would have seen I'm going forward here. I mean, I don't know if we would have introduced some bias that would have prevented us to actually see this type of feature, or the two gradients, for instance, the two changes in phase direction. But that's an interesting question. That's something that we definitely should try. If it doesn't introduce bias, then it would probably help. It would help constrain probably some of these variations a little better.
Okay. Next question is from Luciana Astes, and Luciana is curious, would you say then that the LAB is due to thermal effects, while the G discontinuity reflects compositional changes such as wet versus dry material?
Yeah, that's what I think. I mean, that's what we propose here. Oops. In here, and that the two, basically the thermal effects is basically superimposed to this compositional boundary. Yeah, and unless you were to define this compositional boundary as the lithosphere, I mean, if you were to say that the lithosphere asthenosphere boundary is a wet to dry, for instance, boundary, then the Gutenberg discontinuity is the lithosphere asthenosphere boundary, and this thermal boundary would be something else. But it's a whole matter of nomenclature, really. So I do think there is a compositional boundary inside a high velocity cold top layer.
All right, great. And there's one more question, and it's a follow-up from Amir, who had the question about the joint inversion. And so he asks, what about epicentral distances? If you went ahead with that sort of joint inversion, what sort of epicentral distances for teleseismic earthquakes would you think would be needed?
For the reflectors or for the surface waves?
I would guess the reflectors.
Probably. Yeah, again, that's not my expertise. That's more Nick Schmer's expertise. So I wish he was able to talk if he's there. But to sample the Pacific Ocean, if you imagine how big the Pacific Ocean is and where we have seismic stations and earthquakes, you can imagine that we need quite long epicentral distances. Now, if it was to sample another ocean, then it would be different, I would assume, because the sample point is basically midway between the earthquake and the station.
Right.
I don't have numbers in mind.
Well, that's okay. All right. And so I think last question. Actually, I have two last questions. Okay, so second to last question will be from Ayub Kaviani, and Ayub is asking, do you think we may expect the same anisotropic layering in subduction zones as well?
Well, that's interesting. I mean, if the plate goes down, then there's no reason why it would disappear, as far as I can think, when it's subducting. So if we were able to see it with, I don't know how we would be able to see it, but subduction zones are very messy in terms of seismic waves. There's lots of things going on, it makes them very difficult to study. But so yes, I would say if it starts at the ridge and gets translated away from the ridge, there's no reason why it would disappear before subducting, unless some processes erases it for some reason. But I can't think of one.
All right. And the last question is from Lena Costanza Garcia Cano. And Lena is asking, could it be possible to have any influence in anisotropy from the presence of a mantle plume?
Yes. Actually, so yes. So one thing is, so we have this strong anisotropy, in the middle of the plate. Now the horizontal resolution of the anisotropy model is relatively low, but we have this strong azimuthal anisotropy here that corresponds to ages where we have a plume. And this has been seen with radial anisotropy in the past. Uh, there is a strong radial anisotropy at about the same depth and the same place, and it is due to horizontal flow in the asthenosphere, but it's also possible that this could be a disturbance due to a plume. Yeah, I would say, yeah, it's very possible.
All right. Well, we're out of questions. The only other things that were written in the window were some very complimentary comments for the presenter. So thank you very much, Caroline, from
Thank you.
me, but also the people in the webinar who clearly enjoyed the talk.
Thank you.
And yeah, so thanks very much. And everyone out there, this is I'm going to hit stop on the recording and upload this to YouTube shortly. And then our next webinar is in 2 weeks, and it'll be on lithosphere and upper mantle in the Eastern Mediterranean. So I'd encourage everybody to tune in. So, Caroline, have a great rest of the day. Thanks again.
Thank you, everybody.
Yep. And everyone out there, take care. Bye bye.